is Raziel Maqueda, and I'm a first-year biology major and studying at Foothill College. However, I just transferred to the University of California, Berkeley. My mentor is Andrew Beal, and I worked at the Department of Structural Biology at Stanford University, where our goal was to create an automated cell counting microscope. So, a problem going on right now is that manually cell counting is very time-consuming for many researchers and requires expensive microscopes that can range from 500 to even thousands of dollars that many countries cannot afford. So, our goal became to make a DIY automated microscope that is computer-controlled stage to scanning tissue culture cells in a hemocytometer grid and sending stitch images to a software for accurate cell counting. And that video is just demonstrating some of the inspiration, which was Open Flexure's microscope. So OpenFlexure's design really inspired my 3D printing microscope. But there was also two other designs, which is Puma. However, Puma, I did not tend to use it because the imaging wasn't the best. And then the fully 3D printed microscope, I became inspired by the objective lens that they used resin on. So the big picture significance. The people that it really helps is a clinic star in underserved regions. It could also help many schools and students since this microscope, it would be under $500. It could help students learn more about cells, diseases, or even illnesses as well. So the focus of my research became tissue culture. So pretty much we would work with adhesion and suspension cells. Adhesion cells are pretty much cells that are at the bottom of a growth medium, and suspension cells are pretty much cells that are flowing around a growth medium. The hardwares we were going to use is Raspberry Pi, which pretty much I was planning on using to send commands to a USB for the Arduino. The Arduino is going to control the motors to move the microscope stage around. And then the motorized XYZ stage for the microscope was going to move the hemocytometer slide into position for imaging. And then obviously the microscope would be able to cell count pictures like the one shown in my slide. So as I mentioned earlier, our goal was to create an automated cell counting microscope. However, my internship goal was definitely to analyze as many research papers as I can to grasp really what 3D design I would like to make that was reliable, cost effective, and high quality, accurate for cell counting imaging. So tissue culture. Pretty much I started with adhesion cell passaging. First, we would check confluency by removing the old medium. Confluency is pretty much just checking how many cells are in the growth medium and making sure that we would have to change it every once a week. We would put PBS, which is a salt solution. Then after we put trypsin and EDTA, trypsin pretty much helps detach the cells, while EDTA pretty much just enhances the trypsin to work faster. After we would put in inactivator, we would then transfer it to a sterilized tube, where then it would be in the centrifuge and we remove the supernatant, which is pretty much just a liquid. Then after we would resuspend the cells in a fresh growth medium, and then after we would split the cells into a new flask with a fresh growth medium, and that would be about once a week. And then collecting the cells, we would do the same. We would have to check the confluency, then after transfer it to a sterile tube, and then centrifuge, remove the supernatant, and resuspend the pellet into a fresh growth medium as well. The software we were planning to use is an open source designed to help many researchers, which is Cell Profiler. It has actually helped with many medical advancements, like learning more about leukemia stem cells and tuberculosis research. The hardwares, as I mentioned, I was going to use Raspberry Pi, which pretty much is going to send Python coding to the software Cell Profiler, as I mentioned. And then the Arduino was we were going to use G coding or C++ on the stepper motors or the stepper drivers to help motorize the XYZ stage control. And that's a video demonstrating how adhesion cells are passaged. So materials for our objective lens, we were planning to use resin, as I mentioned, and pretty much we were going to 3D print the resin. Then after we would put an IPA wash. This is a very important step because if there's many monomers that are stuck to the 3D printed resin, and by doing this, it would have a smoother lens. We would spin coat and then UV curing it as well. And then we would spin coat again and then vacuuming and then UV curing again, which would pretty much just help smoothen the top of the resin, make it more clear. So as I mentioned, my inspiration was OpenFlexure's design, and we were going to use their condenser and light source because we realized that it was very reliable and it has actually worked. And pretty much that's just a video of someone building it. And materials and methods for the XYZ stage is pretty much we were going to use the stepper motors in each axis. And the way it would work is that we would flash GRBL to the Arduino. Then after we would use Python coding on the Raspberry Pi to send G coding to a USB serial, where the GRBL would actually just move the axis with microstepping for smooth motion. And then the microscope body, pretty much the 3D printed filament, we were going to use is PLA because not only is it cheap, but it's widely available and it's it helps a lot with good dimensional accuracy. And for the camera, we were planning to use a Raspberry Pi camera V2. The reason why we chose it was because we already knew that it worked with OpenFlexure's design, so we wanted to use that model and put it under our objective lens as well. And then results. So pretty much I reviewed about six articles about 3D printing microscopes and low cost objectives. And pretty much I became inspired by mainly two open sources, which is OpenFlexures, as I mentioned, and the 3D printed microscope that was made in Scotland that had a 3D printed objective lens. I created a material sheet with the cost and also have CAD designs as well. So in conclusion, something that happened was that we were able to confirm our microscope could be built under $500. The next steps definitely would have been ordering the materials, making another spreadsheet maybe, and then assembling the microscope and making sure that the images are clear enough for automated cell counting. If more time, I definitely would have checked more alternatives for the materials, researched more alternatives for the XYZ stage design, and would have definitely tried to make a resin printed objective lens with clear imaging because that is something that was just researched about in July. So it was very new. Some reflections, some challenges I had was not knowing where to look for my articles at first. And that took a bit of time since this research is a very short amount of time. Some successes that I had was definitely learning more about how to make an objective lens out of resin, since I mentioned it's very new. I was able to finalize a material chart, and then make a model for my microscope to 3D print. Some skills I gained was definitely passaging cells, learning how to code Python, and learn how to use CAD. Some personal insights was that I gained more lab work, confidence in lab work, and then I realized the importance of creating low-cost materials to be able to help other countries as well. I would like to thank Sophia Kim for helping me learn more about this opportunity. I would like to thank Jing Chang for helping me learn about how to passage cells. But most of all, I would like to say thank you to Andrew Beal for giving me the opportunity to be able to learn more about coding and learning how to use CAD. Thank you so much for listening.